Hello. We are going to finally finish talking about the SMO Open 2020 paper. As of now, we last stopped at question 18, which had a pile of modular arithmetic and sort of augurs a bunch of not too easy questions in the back half. Now, I'm going to be tackling the remaining questions from the perspective of it being the SMO round 1, because it is undoubtedly going to be difficult to solve many of these questions in a fully rigorous fashion, especially when you are talking about many of these problems being entirely suitable as a round 2 problem as well. For instance, it's this year being 2024, that almost exactly the same question appeared in our SMO Senior Round 2. Question 5, which one would say is obviously meant to take quite a long time. So if you're doing this in a round 2, it can easily take you 45 minutes. Of course, a hint is given here, but it's still not easy. So from a round 1 perspective, what I would be doing is something that is not quite correct, but it turns out to work, and it's something that you can sort of prove in reverse to be correct if you're trying to guess the answer anyway. Now, I know that it says do this, but this is actually correct, just a little bit laborious. So this does work. A bit messy. I've explained how to solve the question and obtain this substitution in my video on the SMO Senior Round 2 2024. So I'm not going to do that. I'm going to talk about sort of the mildly dubious method. And please comment below if you can figure out why this is dubious and why it also can be resolved. Now, the reason why this is not easy to do, even though they only ask about A5, is that the condition is weird. The condition is weird, so I can't quite just compute A3, A4, A5 instantly. But what I can do is I can use the 1 and 2 to just be 1, 2, and I will go with K and K minus 1. Right? So I will use this as a combination that will allow me to write AK in terms of AK minus 1. Obviously, A2 and A1 are already known, so have to do a bit of work, but it is going to be not too bad. So this is the substitution. A1 is 0, so technically this will just disappear. A2 is half. A2 plus 1 is 3 halves. I'll write it in this order. Now, I just need to make AK the subject, so I will reciprocal it. When I reciprocal it, is 1 over 1 plus AK. Reciprocal this as well, and I will just multiply by 2 at the same time. Subtract 1. And then flip it over again. So I've ignored the hint, but this gives me a recurrence, and the recurrence is pretty easy to use. Right? I've got A2 is half, so I can just put in half into here. It gives me 2 over 5 halves. This one would give me 13 over 5 over 14 over 5. And this one would give me 40 over 41. So the answer, which is 1 over 1 minus A5, is equal to 41. I've mentioned that two things are true of this. The first is that this is not technically correct, and the second is that this argument can actually be fixed. So if you want to think about it more carefully, consider what's wrong with this argument and how it can be patched up. But for the purpose of the SMO Open Round 1, this is what I would do. Question 20. Triangle ABC with an in-circle touching at the 3 sides, and then stuff are extended. So let's draw it first. I don't think it is very likely I can make this look true on the first attempt. So I will just draw some random attempt at a diagram where let's just call this ABC. That was a bad idea, wasn't it? These things do not look like the actually, that's not horrible. It's not horrible. Yeah, it's not horrible. Because I want AB. Yeah, I should just swap A and B and then it will look not horrible. Yeah, okay. So I'll swap A and B. Because I was thinking of getting them to intersect. So now this is not horrible, surprisingly. That AB equals to BP equals to PD is at least somewhat believable. So I think I'll live with this. Question did not come with a diagram, so whoever is doing this problem would need to draw it as well. So I am drawing it here. I am now only given one length of CA equals to 9. So that's sort of an irrelevant length. It's just there to be a scale factor. The main thing that I'm asking myself is what's so interesting about these three things being equal? Okay, so this is 9. That's just for later. And I'm supposed to, from here, get the area of the triangle. I don't really know what I want to do with that, but I'm just going to call this length here C in the usual way, and I will call this length A. So in the usual way of your cosine rule and sine rule where you label those A, B, C, except that now C appears a few times. Now there are lots of equations available to us. My intuition here is that I just need two equations because Heron's formula, this is the square of the area, so I really feel like using Heron's formula, would be S minus A, S minus B, S minus C, where B is 9 and the semi-perimeter S is therefore A plus C plus 9 over 2. So I just need to find A and C, and two equations of any type is probably going to be enough. I make no prescriptions as to which are the best equations, but before any equations, I will feed in some raw data, which is the classic fact that in a triangle with an incircle, these are S minus A, S minus B, and S minus C. This is just true because of equal tangents. That means that I practically know every length in the diagram except for DE. I don't have a simple expression for DE, but I have a nice expression for everything else. My equation I'm going to use this time is Menelaus because it is a classic configuration of Menelaus here. It's a classic configuration of Menelaus because I have got these C's here and I would very much like to use them in a ratio. So I'll start off with the most straightforward use of Menelaus, which is in triangle ABC. Menelaus theorem is just looping around the triangle and stopping over at three collinear points that lie on the three sides, which are P, D, and E. So AP over PB times BD over DC times CE over EA equals to 1. AP over PB is 2. The rest of them, if I put them in, I get more good news. Because this cancels off. So 2S minus B equals to S minus A. B is 9. So if you were to simplify this, you get 3A plus C equals to 27. This is equation number 1. When using Menelaus, you don't just have only one configuration you can use it on. This is the key idea for Menelaus. You can use it in different ways. And so I'm going to try to use this on a different triangle. So the other so-called big triangle I see is APE. So I'm going to use APE. Where this time it stops over at points B, D, and C. So AB over BP, PD over DE, and EC over CA equals to 1. Now likewise, this AB over BP is going to cancel, so at least one of them is gone. PD over DE, and then EC and CA. CA is just 9. So therefore, that gives me, well, something involving DE. I don't know what DE is. Oops, wrong direction. C over 9 times S minus C. Unfortunately, now I've got another equation. But fortunately for me, I've gotten the only other thing which I didn't already know in the diagram in terms of lengths. And so therefore I can get myself a third equation using power of a point from point P to the circle. Which is just PF squared equals to PD times PE. I've got all those lengths now, since I was only missing the length of DE. So B is 9, remember, so I have PF, PD is just C, and PE is now this thing here. Now, that means that your two equations and two unknowns are here. You can just substitute C equals to 27 minus 3A into here, and as much as this looks fairly horrible, it simplifies quite nicely. I'm not going to show the simplification because that's not the most exciting part, but if you think of expanding this first, do note that a C squared would cancel out, so it's not as bad as one might fear. I'm just going to give all the values. A will be 8, and then just substitute back. C is 3, S is 10, and then substitute back into the area formula for herons. S minus A, S minus B, S minus C. There may be a smarter way to do this, but if there is a general property that this 3 lengths being equal is supposed to imply, and you don't see it, then you don't see it. So once again, feel free to share if you think that there is a very obvious improvement to how I've solved it. But unfortunately, many SMO open problems are meant to be done by a bunch of length chasing with equations. So I feel this is a good demonstration of that at least. Okay. 21. Acute angled triangle ABC. AB is 75, AC is 53. The external bisector of angle A. So this one needs a little bit of drawing. There's a circumcircle, so I'll draw a circle. Two rather useless looking lengths for now that I don't care too much about. The external angle bisector. Okay, so you can of course first understand what the angle bisector is, which is normally the angle bisector of your triangle, of your angle A in the triangle is here. The external angle bisector is therefore going to be perpendicular to the internal angle bisector because it bisects the exterior angle, and that would mean that these two sum to 90 degrees. Now incidentally, since this is sitting inside a triangle's circumcircle, the internal angle bisector is going to hit it at the midpoint of the opposite arc here, and the external angle bisector is therefore going to meet it at the midpoint of the major arc BC. I don't know if that's important because I have not finished writing the rest of the question down, but I think I will just leave the external angle bisector as it is for the time being. I just know that it hits it at an interesting place. E is actually the midpoint of the arc, so EB is equal to EC. Do I care about that? We will find out soon. But let me just remind myself of that. That is too far from being a straight line. F is the foot of the perpendicular from E onto AB. Find the value of AF times FB. Now this is screaming power of a point, except that there isn't really another line that is going through F for the time being. I also have not seen any useful application of the length 75 and 53. So I think in this case, the information doesn't really make me want to do a giant length chase. The information makes me want to try to do something that makes the 75 and 53 a little bit more useful. And right now I know too few other lengths, and I know basically no other angles. The trick here is to think about what does the external angle bisector also do apart from hitting it at this midpoint down here. Now the external angle bisector is still an angle bisector. Angle bisectors are basically lines of symmetry. They are the lines of symmetry between two other lines, and anything that lies on the angle bisector is equidistant to the two lines. And so as soon as I see the right angle here, which is the distance to one of them, my instinct is I want to draw the right angle to the other one of them, because that would give me congruent triangles. One other funny tidbit is that if you were to look at this question and you see that it gives you the points A, B, C, E, and F, and we are all familiar with the English alphabet, There's a missing letter, isn't there? Every time when you see a question with one conspicuous missing letter, I can guarantee you that the question setter just erased that point from the finished diagram in their solution. So you definitely need to make D appear somewhere, and that is where I will put my D. So it's sort of a tiny little secret. It's possible to circumvent it by a question setter trying to troll you, but it's usually true. So, having constructed that, I have to do something useful with it quickly, otherwise all I've done is just add one more alphabet in a useless place. So, I am, well, first of all, aware that AF times FB, my AF is now equal to AD, so I have sort of got another value. But if we were to now look at this diagram here, and I hope that you can sort of see it, we actually have congruent triangles, one yellow highlighted length and one red length. This is why I like to use color. CDE and BFE. Technically this is SSS after you use Pythagoras to get the third length. But really, we just saw it using color. Two red lengths, two yellow lengths. Hang on, they both have a right angle sitting near to the yellow length. So we get congruent triangles. And wait a moment. When I see congruent triangles, I'm asking myself, which of those things did I not use? And if I am being honest, well, technically, Trigo and Pythagoras will give me everything, but the length that I did not know was equal is just kind of from Pythagoras, right? BF equals to CD is sort of the star piece of information. Because BF is 75 minus AF, and CD is 53 plus AD, and these two are equal. So the implication immediately is that AF equals to AD equals to 11, and FB is just 75 minus 11 is 64. We didn't use powerful point in the end for this solution. We just used the angle bisector to get some equal lengths and then found both AF and FB. Question 22. This is an increasing sequence formed by arranging all the terms in this set in increasing order. The set comprises of the sum of three distinct powers of 2. So add up three different powers of 2. What's the largest value of the integer n such that an is less than or equals to 2020? That means how many terms are under 2020, because it's increasing, so how many can you find before you exceed 2020? This is not easy to do from a pure counting perspective at first glance, because we will be thinking, well, where are the powers of 2 summing up going to like n? There's a lot of sums of powers of 2. So step 1 is that I do need to write the powers of 2 down and see how many of them I need to care about. You can't avoid this because, well, it is always possible to, let's say, have the power of 2 plus 1 plus 2 if it fits under 2020. So write down a list. It ends at 1024 because 2048 exceeds that 2020. Now the interesting thing that I immediately realized is that these are quite small compared to 2020, because 2048 is the next one that just barely exceeds 2020. So this is the easy question that they snuck in between, because once you stare at this and you realize that, oh, there are 11 of these, any 3 out of 11 sum to a term in the sequence. So the answer is just 11 choose 3. There's one more thing to say. From a round 1 perspective, if you just think of this for a second and you're like, yep, I'm okay with that, you can move on. For this one, I will address the loophole, which is that how do we know that they will not repeat? Now, visually, it doesn't look like they will repeat because a power of 2 is very far from the next power of 2. So, but how do we know there isn't some weird way that they can actually repeat? The answer is that these are actually just going to be binary numbers with 3 ones. And we know that binary is a proper base number system where each combination of 1s and 0s will give us a different digit in base 10, so a different number in base 10. And therefore, there are no overlaps, and we can rest easy that all these 165 will really give you different terms. We know they are in the sequence, but we also need to check that they are different terms in the sequence. This is nasty. If it were an open round 2 question, I would handle it very differently from an open round 1 question. Now it says let n be a positive integer and s be the set of all numbers that can be written in this form. This form is a1, a2 plus a2, a3, so it's a bunch of consecutive pairs where the numbers themselves sum to n. So s is the set of all numbers, and I'm told that the average value of s is this. So it depends on n. If, for example, n is 1, then there is nothing to say. If n is 2, the only thing you can get is 1 times 1, and so on. I'm going to try a small value of n and just see how this looks like. Right, so if let's say that I've got n equals to 4, I could just have 2 numbers. 2 times 2 is 4, 1 times 3 is 3. I could also split it into 2 pairs. So if I've got 1, 1 and 2, that's also 3. If I put 1, 2 and 1, that's also 4. This is pretty anticlimactic. Not very exciting. If I split it into 1, 1, 1, 1, do I really need to write that? Well, I'll just write it anyway. That's also, it's just all 3 and 4, isn't it? So that's really anticlimactic. If I have n equals to 5, 4 times 1, 3 times 2 is 6. If I did 3, 1, 1, I've got 1, 3, 1, and 1, 1, 3, that's still the same numbers. If I did this, it still looks the same. But I can also split it now into 2, 1, 1, 1. Now this would give me 5. That's something new. I don't think I need to write every other combination. They're all clearly going to be 5 or 6. And if I did just a bunch of 1s, there would be also 4. So this is going to cover 4, 5, and 6. This one was just 3 and 4. Again, from the perspective of the SMO round 1, my thinking is that there are lots of choices for my A's. I can not only choose what they are, I can choose how many they are, and I can choose what order to put them in. And therefore, I am quite certain that it will be able to cover an entire range. My intuition is therefore that if it can cover an entire range, I just need to know what's the maximum and the minimum. Now, the maximum and the minimum are going to be quite easy to understand, because for the minimum, I'm just going to use a bunch of 1s. And this would give me n minus 1. I'm quite sure I cannot do better or worse than this, depending on the perspective. And for the maximum, I am pretty sure that the best thing I can do is 2 close numbers. For even n, and this for odd n. And the average would just be the average of the front and back. So either this is equal to that 88199, where n is even, or this is equal to 88199, where n is odd. Once more, you can just check the 2. I think there is no point in trying to do some sort of clever modular arithmetic to restrict whether it's even or odd, since it's going to require you to solve one of them for n anyway. So you might as well just pick one of these. If you are fortuitous and you pick the correct one, which is the first one, you're going to end up with n is equal to 838. I'm going to leave you to think about the proof of this as well, because how do we know that we can say this? How do we know we can say this? And how do we know that all values in between are attainable? Each of those does have a justification. The all values are attainable is probably the most tricky one, but each of these are interesting enough that perhaps in a separate video I'm going to just focus on the proof of this question. I'm not going to pause this for a second. You're not going to see the pause, but you'll see a bit of a jump because I'm going to have a lesson now, and I will come back and go over the last 2 questions after my lesson is over. Alright, so I am back in a few seconds of YouTube time, but about 2 hours in real time, to talk about the last couple of questions as well as some parting remarks about this SMO Open 2020. For question 24, we have an easy question again. If you know Cauchy-Schwarz, and this is one of the examples that I put into one of the crash course videos on the SMO Open from a year or 2 ago, because this is sort of a textbook example of Cauchy-Schwarz, or equivalently of QMAM, which is the quadratic mean arithmetic mean. I'll write them both down, the Cauchy-Schwarz statement, and then talk about how it works in a second. So the Cauchy-Schwarz statement is that you're basically trying to get this to be greater than or equal to something. So it will be on the larger side of Cauchy-Schwarz, accompanied by, this is the sum of 4 things. So it should be a sum of 4 things, and this must have a nice geometric mean, which is not hard to do because this has a square, so we can just go with 1, 1, 1, 1, which is the most boring thing ever. All of them can just be therefore reduced down to these as follows. And so therefore this is 4, this 20, 40, 10 and 5 add up to 75, plus the existing 5 is 80 squared, so your minimum value is 80 squared over 4 is 1600. The quadratic mean, arithmetic mean version of it will look sort of similar. The quadratic mean is also sort of equivalent to your expression of variance, for those of you who are doing some statistics already. The quadratic mean, arithmetic mean inequality actually just is equivalent to a statement about variance and mean, which I'll let you think about, but for everyone else's benefit who is not familiar, we shall not talk about statistics. Yeah, so you will see that if you just do a little bit of mental gymnastics, this is equivalent to the Cauchy-Schwarz statement. It will show 20 squared times 4, but that is still the same thing. Now I'll go back and say one more word about Cauchy-Schwarz, because this is often a question that I get asked. What's the way to motivate something like Cauchy-Schwarz, because you find it very difficult to spot? Well, apart from the way that I've just described it, which is like geometric means, let's pick something nice to get the counterpart of it. Cauchy-Schwarz is inherently also a statement about vectors. It's the statement that v dot w, the dot product, is less than or equals to vw, the product of their moduli. The dot product is less than or equals to this, can therefore be the way that you motivate Cauchy-Schwarz. When you see a bunch of sum of squares here, that is related to one of the vector's magnitude, and that vector is surely going to be this one. So we are saying that this dot with something is less than or equals to the modulus of this thing, and the modulus of the other thing. Your choice of the other thing could be any vector, but you need to make sure that this must be possible to compute, because this is what you want to minimize, and you also must make sure that this is computable. Using the initial condition, it is very easy to understand why we would just use 1, 1, 1, 1 on both of this, and it will give you the statement of Cauchy-Schwarz just with some square roots inside. This is probably the alternate motivation that I can provide. Last question is not easy again. It's not easy again because if we are looking at this here, it is quite innocent looking, but despite how innocent it looks, it is not that simple to solve. it asks you for the largest possible value of Q, and if you're thinking that there is some good way to guess it, then you are wrong, because the largest possible value of Q is 290, and just staring at this, I cannot imagine an alternative way of finding this, apart from the intended method. 3994 is 2 times 1997, and 1997 is actually prime, so sorry, you're also not going to be able to find anything much in the factors. Okay, let's start with what I think is quite an instinctive thing to do. Complete the square. Okay, so complete the square. It turns out that this becomes an equation of the form a squared plus b squared equals to 2c squared, which feels like there must be something to it, right? Well, you would not be wrong. Equations in this form can be solved quite nicely. One option is to write two sets of difference of squares, but then that will be like, let's say, a squared minus c squared equals to c squared minus b squared. You will need to do a lot of wrangling with prime factors. It can be confusing, so I shall not do that. The idea is that this is actually one step away from a Pythagorean triple. If you multiply this by 2, now I've made the right side into a square, but the left side is still a sum of squares. And that is something I can apply to here, where a and b are these two things. P minus q minus 3994 squared, and then on the other side it will be 3994 squared. Okay, so this is not an obvious transformation if you have not seen it before. However, it is a good transformation to know, because it's not that you can do this for any other constant apart from 2. So it is actually going to be rather useful to be aware of this. Pythagorean triples is now the next thing that I need to say. X squared plus y squared equals to z squared. The general form of your triples x, y, z is that they are in the form m squared minus n squared, 2mn, and m squared plus n squared times any common factor, which we can call d. In our case here, P and Q, P squared plus Q squared is 3994 times something. At the very least, I do know that these are both even or both odd. They have the same parity, and that would mean that both of these are even. So I can take out one factor of 2. And as I said, 1997 is prime. So therefore, it means that my m squared minus n squared and 2mn and m squared plus n squared times 2 correspond to P plus Q. I should put an absolute value on this thing, because if it's negative, then the absolute value is what is being referred to here. Don't worry too much about this. Again, these two could also be interchangeable. Don't worry too much about it, because we are really going to just find a very short list of m's and n's, since m squared plus n squared is now 1997, and that's not a lot of things to check. That's not a lot of things to check because of the fact that 1997 is a lot smaller than 3994 squared. Take note that m squared plus n squared is 1997. It's not a Pythagorean triple. It's not that you can use this thing a second time because 1997 is not 1997 squared. But it's small enough that you can just list and check. If that sounds, of course, ridiculous, my definition of list and check is not list everything. It's that if we just assume without loss of generality that m is greater than n, which is usually what we have here, since we don't usually need to write negatives separately, it means that your m is pretty big. M is at least 32. So it is feasible to actually just subtract off some squares from 1997 until it just becomes n squared is, well, a square. I'm fast forwarding that process to say that this is going to give you m is equal to 34 and n equals to 29 is the only pair. And so if I were to toss 34 and 29 back into here, 34 squared minus 29 squared times 2, there will be 630. 2 times 34 times 29 times another 2, I should say, is equal to 3944. You're not going to find that randomly, right? It's too much work for sure. So if we are looking at this as my equation, I now have just a couple of cases to check. So P plus Q is 630. P minus Q minus 3994 is negative 3944. Clearly it can't be positive, right? So that much is clear. So this thing is definitely going to be negative. Could also be the other way around. So we have got two possibilities to check, which are not really two possibilities, because to solve for Q, you're just going to subtract the two equations and both of them will give you the same thing, which is Q equals to 290. P has two values which are actually kind of just symmetric. And that brings us to the end of this SMO Open 2022 paper. This is one of the papers where it is quite noticeable that the back end has more difficult questions, although with some easier ones in between. It's also noticeable that the front end is where you'll be doing most of the scoring. So if it's the majority of you who are taking the SMO Open and you're not aiming for, let's say, the top 30, then it is quite likely that if you're able to do more of the first half questions and spot some quicker ones, like let's say this application of Cauchy-Schwarz, you'd have considered yourself to do pretty well. Let me know if you have any questions and any comments. This is not an easy paper, and obviously some of my solutions may not be optimal as well. So do also share if you have got a better solution, and do check out the earlier videos for the first two sections of the paper if you have not already looked at them. Thank you for watching, and see you again soon.